Hello there. Do you know that beneath your feet there's an ocean? Not a small pond or a hidden lake. An ocean, one that holds 3 times more water than every sea, every lake, every river you've ever seen combined. It sits 400 miles down, locked in blue crystal, waiting in the dark. Most people live their entire lives walking on solid ground, never knowing that the biggest reservoir of water on Earth isn't on the surface at all. It's below, way, way below. And tonight, we're going down there together. If this kind of discovery brings you calm, or sparks your curiosity about the hidden wonders beneath our world, hit that like button and subscribe. It helps other science wanderers find their way here too. And tell me in the comments where you're listening from and what time it is there. Let's start with what we know. The ground feels solid, permanent, unmoving. We build our homes on it. We trust it completely. But that solid feeling is hiding something extraordinary. Deep in Earth's interior, trapped in a layer called the transition zone, water exists in amounts that dwarf everything we can see. Picture every ocean you know: the Pacific, the Atlantic, the Indian Ocean. Now triple that volume. That's what's down there. But this isn't water as you know it. There are no underground seas with fish swimming through dark caverns. No massive lakes waiting to be discovered. Instead, the water lives inside rock itself, locked into the very structure of minerals that exist only under crushing pressure and intense heat. The rock holds water the way a sponge holds liquid, except this sponge is made of crystal and exists in conditions that would instantly vaporize any human who tried to visit. The mineral is called ringwoodite. It glows blue because of the water trapped in its molecular structure. Scientists estimate that just 1% of this deep layer contains enough water to fill our oceans 3 times over. 1%. Imagine what the full layer might hold. For most of human history, we had no idea this water existed. We studied the oceans, we measured rainfall, we tracked rivers and mapped lakes. But we missed the biggest water reservoir on the planet because it was hiding in plain sight, buried beneath hundreds of miles of rock. The discovery changed everything we thought we knew about Earth's water: where it came from, how much exists, and how our planet has been recycling it for billions of years. So, as you lie there, comfortable and still, know this: you're not just resting on solid ground. You're floating on top of an ocean larger than anything you can see. An ocean that's been there since Earth was young. An ocean that connects to every drop of water you've ever touched. And we're just beginning to understand what it means. To understand this hidden ocean, we need to go down. Not a little bit down, like a basement or a mine shaft. We're talking about a journey that would take us hundreds of miles into Earth's interior. So, let's descend, together, slowly, and see what we find along the way. The first few feet are easy. Soil, dirt, the ground you've walked on your whole life. It's soft and familiar, full of roots and rocks and the small creatures that call it home. But keep going. Push through the topsoil and you hit something harder. Bedrock. This is where Earth's crust really begins. Solid stone that's been sitting here for millions of years, holding up everything above it. Now we're going deeper. 10 feet down, 20 feet, 50 feet. the temperature starts to rise. For every 100 feet you descend, it gets about 3 degrees warmer. Not much at first, barely noticeable, but it adds up. At this depth, you might find groundwater, the kind that fills wells and springs. This is water most people think of when they imagine underground reserves. But we're not stopping here. Keep going. 100 feet, 200, 1,000. We're passing through layers of rock now, each one telling a story of how Earth formed. Sedimentary layers like pages in a book. Limestone, sandstone, shale. The rocks get older the deeper we go. The pressure increases too. All that weight above us, pressing down. At this depth, the pressure is enough to crush a person instantly. 3 miles down, 5 miles. The deepest mines on Earth only reach about 2 miles down, and even those are at the edge of what's humanly possible. The heat down there approaches 140 degrees. The air pressure would kill you. The rock itself groans and shifts under the strain. But we're going much, much deeper than any mine. 10 miles down now, 20 miles. We've passed through most of Earth's crust. The rock here has never seen daylight, never felt rain. It's been sitting in darkness and heat since the planet was born. The temperature is now hot enough to melt lead. The pressure is thousands of times what you feel at the surface. And still, we're nowhere near our destination. At around 25 miles deep, we hit a boundary. The crust ends, and the mantle begins. This is where Earth's interior truly starts. The rock here isn't quite solid and isn't quite liquid. It flows like honey, but very, very slowly. Over thousands of years, it moves and churns, driven by heat from below. This flowing rock is what moves continents, what creates volcanoes, what shapes the surface of our planet from deep beneath. But here's what you need to know. We're only getting started. The ocean we're searching for sits hundreds of miles below where we are now. To reach it, we have to keep descending through heat that would vaporize metal, through pressure that would compact diamonds, through a layer of Earth that exists in conditions so extreme, matter itself behaves differently. The transition zone, where our underground ocean waits, sits between 250 and 410 miles down. That's the distance from New York to Detroit, from London to Paris and back again. Except, we're not traveling across the surface. We're going straight down through solid rock. And somehow, impossibly, water exists down there in quantities that make our surface oceans look small. So, the question becomes obvious. How? How can water survive in a place like that? How did it get there? And what form could it possibly take? That's where things get truly strange. Here's where everything you think you know about water stops making sense. Because the water in this underground ocean doesn't flow, it doesn't pool, it doesn't splash or ripple or move at all. Instead, it lives inside rock. Actually, inside it, locked into the crystal structure of a mineral that only exists under extreme conditions. That mineral is called ringwoodite. Imagine a sponge. When you dip it in water, the liquid gets trapped in all those tiny holes and spaces. The sponge holds the water, but the water is still water. You can squeeze it out. It's still liquid. Ringwoodite works differently. The water isn't sitting in spaces between the rock. It's woven into the rock itself, trapped between the atoms that make up the crystal. The hydrogen and oxygen atoms become part of the mineral's structure. They can't escape, they can't flow, they just exist there, locked in place by chemistry and pressure. Think of it like this. You know how salt dissolves in water? The salt breaks apart and mixes with the water molecules. Ringwoodite does the opposite. It grabs water molecules and holds them inside its crystal lattice. The technical term is that water becomes a component of the mineral. But simply put, the rock drinks the water and holds it so tightly that it becomes part of the stone itself. This isn't like a cave with an underground stream running through it. This isn't water trapped in pockets or cracks in the rock. This is water that has become one with the mineral. If you could somehow hold a piece of ringwoodite in your hand, which you can't because it only forms hundreds of miles underground, it would look like a blue crystal. Solid, hard, stone. But inside that crystal, at the molecular level, water exists. Billions upon billions of water molecules, frozen in place not by cold, but by the structure of the rock itself. The blue color comes from the water. Pure ringwoodite without water would look different. But when it contains water, it takes on this distinctive blue shade. Scientists can actually tell how much water the crystal holds by how blue it appears. The deeper the blue, the more water is trapped inside. And down in the transition zone, some of these crystals are very, very blue. Now, here's what makes this even more remarkable. The amount of water that ringwoodite can hold is staggering. By weight, the mineral can be about 1 to 3% water. That doesn't sound like much until you remember the scale we're talking about. The transition zone is a shell of rock that wraps around the entire planet. It's hundreds of miles thick, billions and billions of tons of rock. If just a small fraction of that rock is ringwoodite, and if that ringwoodite holds even 1% water, you end up with more water than exists in all the oceans combined. Scientists used to think Earth's water was mostly on the surface. We could see the oceans, we could measure them, we understood lakes and rivers and ice caps. But nobody imagined that the largest water reservoir on the planet was locked inside crystal hundreds of miles down. It was hidden in a form we didn't even think to look for. But ringwoodite doesn't form just anywhere. You can't make it in a lab easily. You can't find it on the surface. It only exists in a very specific range of depths, where the temperature and pressure are just right. Too shallow, and the conditions aren't extreme enough. Too deep, and the mineral transforms into something else. The transition zone is the sweet spot, the only place on Earth where ringwoodite can exist naturally. And that's exactly where our underground ocean lives, trapped in blue crystal, waiting in the dark. Ringwoodite is strange, not just because it holds water, but because of how it forms and what it needs to exist. To understand this crystal, you need to understand the extreme world it lives in, a world where the rules change completely. At the depths where ringwoodite forms, the pressure is intense, beyond anything we experience on the surface. Imagine taking all the weight of the atmosphere above you and multiplying it by hundreds of thousands. That's the kind of pressure we're talking about. It's enough to change the very nature of rock. Minerals that exist near the surface can't survive down there. they collapse, they transform, they become something new. Ringwoodite is actually a transformed version of a mineral called olivine. Olivine is common. It exists all over Earth's upper mantle. It's a greenish mineral that forms in volcanic rock. But when olivine gets pushed deep enough, when the pressure becomes overwhelming, its atomic structure can't hold. The atoms rearrange themselves into a tighter, denser pattern. And when they do, olivine becomes ringwoodite. This transformation only happens in a specific zone. Between about 250 and 410 miles deep. Shallower than that, the pressure isn't strong enough. Deeper than that, ringwoodite itself transforms into other minerals. So there's this narrow band, this shell around the planet, where ringwoodite can exist. And that's where our water hides. The temperature down there is brutal. We're talking about heat that reaches 2,700 degrees Fahrenheit in some areas. Hot enough to melt rock if it weren't for the pressure holding everything together. At the surface, water boils at 212 degrees. It turns to steam and disappears into the air. But down in the transition zone, the pressure is so immense that water can't boil. It can't escape. Instead, it gets squeezed into the crystal structure of ringwoodite and stays there. Think about a pressure cooker. Water inside it can get much hotter than normal without boiling because the pressure keeps it liquid. The transition zone works the same way, but taken to an extreme. The water trapped in ringwoodite exists at temperatures that would normally destroy it. But the pressure changes the rules. It forces the water to behave differently, to exist in a form that shouldn't be possible anywhere else. The blue glow of water-rich ringwoodite isn't just pretty, it's proof. When scientists study tiny fragments of this mineral, they can see that color and know immediately that water is present. The crystal wouldn't look that way without it. Every shade of blue tells a story about how much water the rock is holding, how tightly it's packed, how stable it is at those depths. What makes ringwoodite special is its structure. At the atomic level, it's arranged in a way that creates tiny spaces. Spaces just the right size to trap water molecules. When water gets forced into those spaces by the incredible pressure, it fits perfectly. Like a key in a lock, the hydrogen and oxygen atoms settle into the crystal lattice and become part of it. They're not free. They can't move, but they're there, preserved in stone. This is why scientists got so excited when they found evidence of ringwoodite containing water. It meant that Earth has a way to store massive amounts of water deep underground. A storage system that's been working for billions of years. The transition zone isn't just a layer of hot rock. It's a reservoir, a bank account for water that Earth has been depositing into since the planet was young. And because ringwoodite is stable at these depths, the water stays there. It doesn't escape. It just waits, locked in blue crystal, part of a cycle we're only beginning to understand. For years, scientists suspected that water might exist deep in Earth's mantle. They had theories, mathematical models, seismic data that hinted at something unusual in the transition zone. But they had no proof, no physical evidence. They couldn't just drill down 400 miles to check. The technology doesn't exist. So they waited. And then, in 2014, a tiny damaged diamond changed everything. The diamond was small, barely 3 millimeters across. Not the kind of gem you'd put in a ring. It was brown and flawed, full of imperfections. Most jewelers would have thrown it away, but to scientists, it was priceless. Because inside that diamond, trapped in one of its flaws, was a fragment of ringwoodite. The first piece of this deep mineral ever found on Earth's surface. Diamonds form deep underground, much deeper than most rocks we ever see. They're created under intense heat and pressure, in the mantle far below the crust. And sometimes, very rarely, they get brought to the surface through volcanic eruptions, not the slow, oozing lava flows you might picture. We're talking about explosive eruptions that punch through hundreds of miles of rock in a matter of hours. These eruptions create pathways called kimberlite pipes, narrow channels that reach from deep in the mantle all the way to the surface. This particular diamond came from Brazil. Someone found it in an area known for kimberlite deposits. They sold it as a low-quality stone, never knowing what it carried inside. Eventually, it ended up with researchers who were studying diamonds from deep sources. They wanted to know what diamonds could tell them about Earth's interior. So, they started examining it closely. Using specialized equipment, they looked inside the diamond's structure, and there, in a tiny inclusion, they saw it. A fragment of ringwoodite. The color was right. The crystal structure matched what they expected. But the real shock came when they analyzed it further. The ringwoodite contained about 1.5% water by weight. That might sound tiny, but remember the scale. If this sample was representative of the transition zone as a whole, it meant there was more water down there than in all the surface oceans combined. The diamond had acted as a time capsule. It formed deep in the transition zone, trapping a piece of ringwoodite inside itself as it crystallized. Then it got caught up in a violent eruption. Magma blasted it upward through the mantle, through the crust, and onto the surface. The whole journey probably took less than a day. And because diamonds are incredibly strong, the ringwoodite inside stayed protected. It didn't break down. It didn't transform. It arrived at the surface exactly as it was hundreds of miles below. Think about what that means. This tiny crystal traveled further than most rocks ever do. It came from a place no human will ever visit. A place where the pressure would crush steel and the heat would melt stone. And it brought evidence. Proof that water exists in Earth's deep interior in quantities we never imagined. Before this discovery, the underground ocean was just a theory, a possibility, something that might be true based on seismic readings and computer models. But now scientists could hold the proof in their hands. They could study it, measure it, confirm that yes, water really does exist, locked in rock hundreds of miles down. The diamond didn't lie. It couldn't. It was a messenger from the deep, carrying news that changed how we understand our planet. Other diamonds have been found since then. Other fragments of deep minerals containing water. Each one adds to the story. Each one confirms what that first diamond revealed. Earth's interior isn't dry. It's not just hot rock and metal. It's holding water, vast amounts of it. And that water has been there, cycling through the deep for as long as Earth has existed. The diamonds keep coming up, one at a time, each one a small window into the hidden ocean below. Let's talk about size, real size, the kind of numbers that break your brain a little. Because when scientists say this underground ocean is bigger than all surface water combined, they're not exaggerating. They're actually being conservative. Take every ocean you know, the Pacific, which covers nearly half the planet's water surface, the Atlantic, stretching between continents, the Indian Ocean, the Arctic, the Southern Ocean, wrapping around Antarctica. Add them all together. Every wave, every drop, every cubic mile of seawater, from the surface down to the deepest trenches. You've got about 320 million cubic miles of water. Now add the lakes. Every lake on Earth, the Great Lakes, the African Rift Lakes, Lake Baikal in Russia, the deepest lake in the world. All of them. Add the rivers, the Amazon, the Nile, the Mississippi, every stream and creek and waterway on the planet. Add the ice caps, Antarctica and Greenland, every glacier, every ice sheet, all the frozen water in the world. Put it all together and you have Earth's surface water, everything we can see, everything we've mapped and measured and sailed across, everything that makes our planet look blue from space. It's a lot of water, more water than you could ever wrap your mind around, enough to cover the entire planet in an ocean over 2 miles deep if you spread it out evenly. And the transition zone holds 3 times that much. 3 times. Locked in ringwoodite hundreds of miles underground. If you could somehow extract all the water from the transition zone and pour it onto Earth's surface, the oceans would rise. The continents would flood. Everything we know would be underwater, drowned beneath a layer of water so deep it would reshape the planet. But here's what makes it even harder to grasp. That 3 times estimate is conservative. It's based on the assumption that only a small fraction of the transition zone contains water-bearing ringwoodite. Scientists think the layer might hold anywhere from 1 to 3% water by weight. But the transition zone is massive. It's a shell of rock wrapped around the entire planet, stretching from about 250 miles deep to 410 miles deep. That's a layer 160 miles thick, circling the whole Earth. Imagine trying to measure how much rock that is, how much volume, how much weight. The numbers become meaningless because they're so large. But even if just a tiny percentage of that rock contains water, the total amount is staggering. Some estimates put it as high as 10 times the surface oceans. 10 times. Everything you can see from space, multiplied by 10, hiding in blue crystal beneath your feet. The Pacific Ocean alone covers 63 million square miles. It's the largest thing on Earth's surface. You could fit all the continents inside it with room to spare. And yet, compared to the water in the transition zone, it's small. The underground ocean doesn't have boundaries. It doesn't have shores. It's everywhere, beneath every continent, beneath every ocean, a hidden layer of water locked in stone. Think about standing at the beach, watching waves roll in, feeling the spray, knowing that the ocean in front of you stretches for thousands of miles. Now imagine that same ocean, tripled in size, existing as a solid layer deep underground. Not liquid, not flowing, but present, real, holding more water than every river that ever flowed into that ocean, more water than every rainstorm that ever fell on it, more water than all the ice that ever melted into it. And nobody knew it was there. For all of human history, we looked at oceans and thought they were the bulk of Earth's water. We worried about droughts and freshwater shortages, never realizing that the planet has been hoarding water in its depths all along. The underground ocean doesn't care about coastlines or weather patterns. It just exists, quiet and permanent, larger than anything we can see, hidden in a layer we can't reach. The transition zone isn't just a random layer of Earth. It's special. A place where the rules of geology shift, where minerals transform, where pressure and temperature reach a perfect balance that creates conditions unlike anywhere else on the planet. It sits between two other major layers. Above it is the upper mantle, where rock flows slowly over millions of years, driving plate tectonics and creating the forces that shape our surface. Below it is the lower mantle, even deeper and more compressed, where rock behaves in ways we're still trying to understand. The transition zone is the bridge between them, a boundary layer where everything changes. The depth range matters, from about 250 miles down to 410 miles down. Not deeper, not shallower, just that specific range. And the reason is pressure. At 250 miles, the pressure reaches a point where olivine, that common green mineral from the upper mantle, can no longer hold its structure. The atoms get squeezed so tightly that they have to rearrange. They form ringwoodite. The transformation happens across a boundary called a discontinuity, a place where seismic waves suddenly change speed because the rock itself has changed form. At 410 miles, another discontinuity happens. The pressure becomes too much, even for ringwoodite. It transforms again into other minerals with even denser structures. Minerals that can't hold water the same way. So, ringwoodite only exists in that narrow band, that window between crushing and absolutely crushing pressure, and that's where the water accumulates. The temperature in the transition zone ranges from about 2,200 degrees Fahrenheit at the top to over 2,700 degrees at the bottom. Hot enough to glow if you could somehow see it. Hot enough to melt most metals instantly. But the pressure keeps everything solid. It forces the atoms together so tightly that they can't move freely. The rock can't melt, even though it's hot enough to. It stays crystalline, structured, and those structures can trap water. Think of it like a vice. When you squeeze something in a vice, you can compress it far beyond its normal state. The transition zone is like that, but instead of a mechanical tool, it's the weight of hundreds of miles of rock pressing down from above. That weight creates pressure that changes the fundamental properties of matter. Water that would boil away at the Earth's surface stays locked in place down there. It has nowhere to go. The pressure won't let it escape. Seismic waves tell us about this layer. When earthquakes happen, they send waves rippling through Earth's interior. Those waves travel at different speeds through different materials. When scientists measure how fast seismic waves move through the transition zone, they notice something odd. The waves slow down slightly. They behave as if the rock is a bit less dense than expected, or as if something is affecting how they travel. That something is water, Water in ringwoodite changes how seismic waves move through the rock. It creates a signature, a pattern that scientists can detect from the surface. By studying thousands of earthquakes and measuring how their waves travel through the deep earth, researchers have mapped where water might exist in the transition zone. And the answer is almost everywhere, not uniformly. Some areas have more than others, but it's widespread, global, a layer of wet rock encircling the entire planet. The transition zone doesn't connect to the surface in any direct way. There are no cracks or channels that let water flow up and down. It's isolated, separated from the oceans above by hundreds of miles of solid rock. And yet, water gets there. Somehow, over geological time, water from the surface makes its way down. It gets recycled into the deep through processes we're still figuring out. And once it's there, locked in ringwoodite, it stays for millions of years, maybe longer. This layer is stable. It doesn't churn rapidly like the upper mantle. It doesn't shift quickly. It sits there, a quiet reservoir, holding more water than we ever imagined possible. The perfect conditions for storage. Hot enough and pressurized enough to keep water trapped in crystal, but stable enough that the water doesn't get destroyed or released, just held, suspended in the deep, waiting. So, how does water from the surface end up 400 miles underground, trapped in crystal? The answer lies in one of Earth's most powerful processes: plate tectonics, the slow dance of continents and ocean floors that's been happening for billions of years. Picture the ocean floor. It's not static. It's constantly being created at underwater mountain ranges called mid-ocean ridges. Hot magma rises from the mantle, cools, and forms new seafloor. That new rock spreads outward, pushed by more magma rising behind it. The seafloor moves, inches per year, slowly but constantly. Eventually, that moving seafloor runs into a continent or another plate. And when it does, something has to give. The denser ocean plate slides beneath the lighter continental plate in a process called subduction. It gets pushed down, forced back into the mantle, recycled. But here's the key part. That ocean floor isn't dry. It's been sitting at the bottom of the ocean for millions of years. Seawater seeps into cracks in the rock. It reacts with minerals. It gets trapped in the crystal, structures of rocks near the surface. The seafloor becomes hydrated, wet, not soaking wet like a sponge, but chemically bound water locked into the minerals. When that wet rock subducts, it takes the water with it. Down it goes, pulled by its own weight, sliding beneath the continent. 10 miles deep, 20 miles, 50. The rock heats up as it descends. The pressure increases, and some of that water gets squeezed out. It rises back up, causing the volcanism we see at subduction zones. The ring of fire around the Pacific. The volcanic chains that mark where plates collide. That's water being released from descending rock, triggering melting in the mantle above. But not all the water escapes. Some stays locked in the minerals. It goes deeper, past the volcanic zone, past the crust, into the upper mantle, and then deeper still. The rock that's subducting doesn't stop at shallow depths. it keeps going, driven by gravity and the push of more seafloor behind it, down through the upper mantle, heading toward the transition zone. At around 250 miles, something changes. The pressure becomes intense enough that minerals in the subducting slab transform. Olivine becomes ringwoodite. And when that transformation happens, the water that was trapped in other minerals gets transferred. Ringwoodite is better at holding water than the minerals above it. So it absorbs the water, locks it in, holds it in that blue crystal structure we talked about. This process has been happening for a long time, since Earth had oceans and plate tectonics. For billions of years, ocean floor has been subducting, carrying water down, depositing it in the transition zone, layer after layer, slab after slab. The water accumulates, not quickly, but steadily. Over hundreds of millions of years, the transition zone has filled with water like a reservoir slowly filling with rain. Think about the scale. Earth's entire ocean floor gets recycled every 200 million years or so. That means the seafloor you're standing on, if you're near a coast, didn't exist when dinosaurs walked the Earth. It's been created since then, and the seafloor that existed back then has been subducted, pushed down, recycled into the mantle, taking water with it. Some of that ancient seawater from the age of dinosaurs might still be down there, trapped in ringwoodite, locked 400 miles underground. Water that once felt sunlight, that once had waves, that once held prehistoric marine life. Now it's part of the rock, part of the deep, transformed but not destroyed. This is how Earth recycles its water on the grandest scale, not just through rain and rivers and evaporation, but through the slow movement of continents, through subduction zones that drag water into the depths, through the transformation of minerals under pressure. The planet has been doing this since it was young, building an underground reservoir, one subducting slab at a time. And that reservoir is still growing. Every subduction zone on Earth today is carrying water down, adding to the transition zone. The process never stops. Time moves differently when you're talking about Earth's water cycle. Not the quick cycle we learn about in school, with rain and rivers and clouds. That cycle happens in days or weeks. But the deep water cycle, the one that involves the transition zone, operates on a time scale that's almost impossible to grasp. We're talking about hundreds of millions of years, billions even. The water in the transition zone didn't get there overnight. It accumulated slowly, very slowly. Each subducting slab carried a small amount down. Over time, those small amounts added up. Think of it like filling a bathtub with an eyedropper. One drop doesn't make a difference. 1,000 drops barely registers. But keep going for long enough, and eventually the tub fills. The transition zone has been collecting drops for most of Earth's history. Scientists estimate that Earth is about 4.5 billion years old. The oceans formed not long after that, maybe 4 billion years ago. And plate tectonics, the engine that drives subduction, started sometime in Earth's first billion years. So, for roughly 3 to 4 billion years, water has been cycling into the deep. That's enough time for the entire ocean to be subducted and replaced dozens of times over. But here's what makes it interesting. The water doesn't just go down, it also comes back up. Not the same water exactly, and not on the same timescale, but there's an exchange happening, a slow conversation between the surface and the deep that's been going on since Earth was young. Water gets released from the transition zone through volcanic activity. When rock in the mantle rises toward the surface, it experiences less pressure. Minerals that were stable at depth become unstable. They break down, they transform, and when they do, the water they were holding gets released. That water rises with the magma. It becomes part of volcanic gases. It erupts onto the surface as steam. Eventually, it condenses and joins the surface water cycle again. This happens at mid-ocean ridges, where new seafloor forms. It happens at volcanic hotspots like Hawaii. It happens anywhere magma reaches the surface. Water that spent millions of years trapped in ringwoodite finds its way back to the oceans. Not quickly, not all at once, but gradually. The deep exhales water back to the surface, just as the surface sends water down through subduction. The timescale for this exchange is staggering. A water molecule at the surface might take 3 million years to complete a full cycle. Down through subduction, trapped in the transition zone, eventually incorporated into rising mantle rock, released through volcanism, back to the surface. That's longer than the entire age of dinosaurs, longer than the time it took for complex life to evolve on land. One complete cycle of water through Earth's interior takes geological epochs, and during that time, the water changes form repeatedly. It starts as liquid ocean water, gets bound into minerals in the sea floor, transforms into different mineral structures as it descends, becomes part of ringwoodite in the transition zone, gets released as the minerals break down, rises as a component of magma, erupts as steam, condenses back to liquid, the same water, but never staying in the same form for long. Some of the water in today's oceans has been cycling for billions of years. It might have been part of the first oceans that formed when Earth was young. It cycled down into the mantle early in Earth's history, spent 1 billion years in the deep, rose back up, cycled down again, rose again, over and over. That glass of water you drank today might contain molecules that have been to the transition zone and back multiple times. Molecules that are older than any rock you'll ever touch. The underground ocean isn't separate from the surface ocean. They're connected, part of the same system, the same water, just distributed differently. Some at the surface where we can see it, some locked deep underground where it waits. The balance between them has probably shifted over time. Maybe early Earth had less water in the transition zone because the process was just getting started. Maybe the underground reservoir has been growing steadily for billions of years. Or maybe it reached an equilibrium long ago, where the rate of water going down equals the rate coming back up. We don't know for sure, but we know the exchange is real. We know it's been happening longer than anything else we can point to, longer than mountains have existed, longer than continents have had their current shapes. The water cycle isn't just rain and rivers. It's a planetary process that operates on the deepest levels and the longest timescales imaginable. To really understand how water survives in the transition zone, we need to talk about the two forces that rule the deep: temperature and pressure. They work together in ways that seem impossible. They create conditions that shouldn't allow water to exist. And yet, somehow they do. Start with temperature. At 250 miles down, where the transition zone begins, the rock reaches about 2,200 degrees Fahrenheit. That's hot enough to melt aluminum instantly, hot enough to turn sand into glass, hot enough that if you could somehow put your hand there, it would vaporize before you even felt the pain, and it only gets hotter as you go deeper. By 410 miles, at the bottom of the transition zone, temperatures approach 2,700 degrees. That's nearly half the temperature of the sun's surface. Water can't exist at those temperatures. Not normally. At sea level, water boils at 212 degrees. It turns to steam and disappears into the air. Even in a sealed container, raise the temperature high enough and water breaks apart completely. The molecules split into hydrogen and oxygen. The water ceases to be water. So how does it survive thousands of degrees hotter than boiling? The answer is pressure. Enormous, crushing, unimaginable pressure. At the transition zone, the weight of hundreds of miles of rock bears down from above. Every square inch experiences millions of pounds of force. To put that in perspective, at sea level, air pressure is about 14.7 pounds per square inch. That's the weight of the entire atmosphere pushing down on you. In the transition zone, the pressure is over 1 million times that, maybe 2 million times. The numbers become hard to even conceptualize. That pressure changes everything. It changes how atoms behave. It changes what states of matter are possible. At the surface, water has 3 basic states. Solid ice below 32 degrees. Liquid water between 32 and 212 degrees. Steam above 212 degrees. But those temperature limits only apply at normal pressure. Change the pressure and the rules change too. In the transition zone, pressure is so intense that water can't boil. It can't turn to steam. The molecules are held so tightly together by the surrounding force that they can't escape into a gas phase. Even at 2,000 degrees, the pressure keeps them condensed, trapped, unable to expand and vaporize the way they would at the surface. But it goes further than that. The pressure doesn't just keep water from boiling. It forces water to do something it wouldn't normally do. It pushes water molecules into the crystal structure of ringwoodite. At normal pressure, water and rock are separate. Water flows around rock. It sits in cracks and pores, but it doesn't become part of the rock's atomic structure. Under extreme pressure, though, the water gets squeezed into spaces between the atoms in the crystal. It becomes incorporated, locked in place not just by chemistry, but by sheer physical force. Think of it like trying to push air into a solid block of wood. At normal pressure, you can't do it. The air bounces off. But if you could apply enough pressure, if you could squeeze hard enough, you could force air molecules into the tiny spaces in the wood's structure. That's essentially what's happening in the transition zone. Pressure forces water into rock in a way that wouldn't be possible anywhere else. Temperature and pressure also work against each other in interesting ways. Heat makes atoms vibrate. It makes them want to move, to expand, to break free from whatever's holding them. But pressure does the opposite. It compresses. It holds everything tight. It prevents movement. In the transition zone, these two forces are in constant tension. Heat trying to destroy the water, pressure trying to preserve it, and somehow they balance. The pressure wins just enough to keep water trapped in ringwoodite, but the heat wins just enough to keep everything dynamic, to allow the slow transformations that let water cycle through the deep over millions of years. Without this precise balance, the underground ocean couldn't exist. If the pressure were lower, the heat would drive all the water out. It would rise to the surface as steam. If the pressure were higher, the water might get crushed into something else entirely, a different form of matter that we don't even see at Earth's surface. The transition zone sits in a sweet spot, the only place on the planet where temperature and pressure create exactly the right conditions for rock to hold water in such massive quantities. It's a delicate dance between two opposing forces, and it's been performing for billions of years. When scientists confirmed that water exists in massive quantities deep in Earth's mantle, it wasn't just an interesting fact. It was a revelation that changed entire fields of study. It rewrote textbooks. It forced us to reconsider some of the most basic questions about our planet. Where did Earth's water come from? Has the amount changed over time? And what does it mean for how our planet works? Before the discovery, the leading theory about Earth's water went something like this. Earth formed hot, very hot, so hot that any water present during the planet's formation would have boiled away into space. The early Earth was essentially dry. Then, millions of years later, comets and asteroids brought water from the outer solar system. They crashed into Earth, delivering ice that melted and formed the oceans. Over time, enough impacts happened that water accumulated on the surface. This was called the late veneer theory. It made sense. Comets are basically dirty snowballs. Asteroids from the outer solar system contain ice. If enough of them hit Earth, they could explain where the oceans came from. Scientists could point to evidence of ancient impacts. They could calculate how much water comets might carry. The theory worked mathematically, but the underground ocean changed that calculation. If Earth has 3 times more water locked in the transition zone than exists on the surface, that's a lot of water to explain through comet impacts alone. You'd need an enormous number of impacts, far more than the evidence suggests actually happened. The math started to break down. The new understanding is simpler. Earth's water might have been here all along. When the planet formed 4.5 billion years ago, water was part of the material that came together. Not as liquid water, obviously. The early Earth was too hot for that. But as water locked into minerals. Just like ringwoodite holds water today, other minerals in the early Earth held water too. As the planet cooled, some of that water was released to the surface. It formed the oceans, but a lot of it stayed deep, trapped in the mantle, cycling through plate tectonics once they started. This means Earth's water is native, original. It's been part of the planet since the beginning. The oceans didn't need to be delivered from space. They came from inside, from the deep interior, releasing water over time through volcanic activity. The underground ocean isn't a separate thing. It's the main reservoir, the source. The surface oceans might just be overflow, water that escaped from the deep and hasn't cycled back down yet. This has huge implications for understanding Earth's history. It means water has been influencing our planet's geology from day one. Water in the mantle affects how rock melts. It lowers the melting point of minerals. That influences volcanism, plate tectonics, the creation of continents. Everything about Earth's surface geology might be connected to water in the deep. Without that water, Earth might look completely different. No oceans, no plate tectonics, maybe no life. The discovery also helps explain something scientists noticed but couldn't account for. Earth's surface water levels have been relatively stable for billions of years. The oceans haven't grown dramatically. They haven't shrunk dramatically. Despite constant evaporation, despite water being carried down into the mantle through subduction, the amount at the surface stays roughly the same. Why? The underground ocean provides an answer. It's a buffer, a reservoir that absorbs excess water when there's too much and releases water when there's too little. The transition zone and the surface exist in a kind of equilibrium. Water cycles between them, but the total amount in each layer stays balanced over long periods. This stability is part of why Earth has been habitable for so long. The water doesn't disappear. It doesn't all get locked away in the deep. It cycles. It maintains balance. Understanding this changes how we think about other planets too. Mars, for example, once had liquid water on its surface. Rivers carved valleys. Lakes existed. But now, the surface is dry. Where did the water go? Some evaporated into space, but maybe some went underground. Maybe Mars has its own version of a transition zone, holding ancient water in minerals deep below the surface. We don't know yet, but the discovery of Earth's underground ocean makes it seem possible. Venus is another mystery. It's similar in size to Earth. It probably formed with similar amounts of water, but today its surface is a hellscape with temperatures hot enough to melt lead. No liquid water anywhere. What happened? Did Venus lose all its water to space? Or is some of it still there, hidden deep inside like Earth's? We can't answer that yet, but knowing Earth hides most of its water underground makes us look at other planets differently. The underground ocean didn't just change Earth science, it changed planetary science, astrobiology, our understanding of what makes a planet habitable. Water isn't just about oceans and rain, it's about what's hidden in the deep, and that might be true everywhere. Once scientists understood that Earth hides most of its water deep underground, a new question emerged. If it happens here, does it happen elsewhere? Could other rocky planets have their own hidden oceans locked in their mantles? The answer is changing how we search for life beyond Earth. Start with Mars. The red planet once had rivers. We can see the dried up channels carved into its surface. It had lakes, maybe even an ocean covering part of its northern hemisphere. But today, Mars is dry. The surface is a frozen desert. The atmosphere is thin. Any liquid water would evaporate almost instantly. So, where did all that water go? Some escaped into space. Mars has weak gravity and no magnetic field to protect its atmosphere. Solar wind stripped away much of the air, and water vapor went with it. But scientists don't think all the water escaped. Some of it might still be there, frozen at the poles, trapped as ice beneath the surface. And maybe, just maybe, locked in minerals deep underground. Mars has a mantle. It has an interior structure similar to Earth's, just smaller and cooler. If water cycled into Mars's deep interior billions of years ago, when the planet was more geologically active, some might still be there, trapped in minerals that hold water the same way ringwoodite does. We can't drill into Mars to check. We can't study its deep interior directly. But the possibility exists. Mars might have its own underground ocean, left over from when the planet was wet and warm. Then there's Venus, our sister planet, almost the same size as Earth, probably formed with similar amounts of water. But today, Venus is a hellish world. Surface temperatures reach 900 degrees. The atmosphere is thick with carbon dioxide and sulfuric acid clouds. No water anywhere we can detect. Venus should have had oceans, but they're gone. The leading theory is that Venus lost its water through a runaway greenhouse effect. The planet got too hot. Water evaporated. Sunlight broke the water vapor into hydrogen and oxygen. The hydrogen escaped to space. Over time, Venus dried out completely. But that's based on what we see at the surface. What about deeper? Could Venus have water locked in its mantle? We don't know. Venus's interior is a mystery. Its thick atmosphere makes it hard to study with radar. We've never measured what's in its deep mantle. But if Earth hides most of its water underground, maybe Venus does too. Now, let's go further out, to the icy moons of the outer solar system. Europa, orbiting Jupiter. Enceladus, orbiting Saturn. These worlds are nothing like Earth. They're small, cold, covered in ice. But beneath that ice, liquid oceans exist. We know this from gravity measurements and observations of geysers shooting water into space. Europa's ocean might be 60 miles deep. Enceladus has active water plumes erupting from cracks in its ice shell. These aren't underground oceans in the same sense as Earth's. They're liquid water oceans beneath ice crusts. But they prove that water can hide in places we don't expect. That the visible surface doesn't tell the whole story. Europa and Enceladus look frozen and dead from above. But below, there's water, possibly warmed by tidal heating as their parent planets squeeze and flex them. That water could potentially harbor life. The discovery of Earth's underground ocean makes scientists think differently about where to look for water on other worlds. We used to focus on surfaces. Does the planet have rivers, lakes, oceans we can see? But now we know to look deeper, to consider what might be hidden in the interior. Water doesn't have to be on the surface to exist. It doesn't have to be flowing to be important. This opens up possibilities for where life might exist. Life needs water, but it doesn't necessarily need surface water. If Mars has water locked in its mantle, could there be pockets where that water is released? Could there be subsurface environments where liquid water exists, fed by the deep reservoir? We don't know yet, but it's worth looking. The same goes for planets around other stars. We've discovered thousands of them. Rocky planets similar in size to Earth. We try to figure out if they have atmospheres, if they're in the habitable zone where liquid water could exist on the surface. But maybe we're thinking too narrowly. Maybe some of those planets have no surface water, but massive underground reservoirs. Maybe they're habitable in ways we haven't considered. Earth's underground ocean teaches us that planets are more complex than they appear. That water, the key ingredient for life as we know it, can exist in hidden forms. That the absence of surface oceans doesn't mean a planet is dry. It just means we need to look deeper. And as we explore the solar system and beyond, that's exactly what we're learning to do. The underground ocean has been there for billions of years. But nothing lasts forever. So, what happens to it? Where does it go from here? To answer that, we need to think about Earth's future, not the next 100 years, or even the next 1,000. We're talking about millions and billions of years into the future. Earth is cooling, very slowly. When the planet formed, it was molten, a ball of liquid rock. Over time, heat has been escaping into space. The interior has been cooling down bit by bit. This process will continue. In 1 billion years, Earth will be cooler than it is today. In 2 billion years, cooler still. Eventually, maybe in 4 or 5 billion years, the interior will cool enough that plate tectonics slows down significantly. Maybe stops altogether. When that happens, the water cycle changes. No more subduction zones pulling water into the deep. No more volcanic activity releasing water back to the surface. The exchange between the underground ocean and the surface oceans would grind to a halt. The water would become trapped wherever it is. What's in the transition zone stays there. What's on the surface stays there. The two reservoirs would be cut off from each other. But that's a long way off. For now, the cycle continues. Water keeps descending through subduction. It keeps rising through volcanism. The underground ocean keeps exchanging with the surface. And that will probably continue for at least another 1 billion years, maybe 2. Earth's engine is still running. The mantle is still hot. The plates are still moving. In the shorter term, over the next few million years, the underground ocean will probably grow slightly. Not by a huge amount, but measurably. More water gets subducted than gets released in any given year. The balance tips slightly toward the deep. Over time, that means more water accumulates in the transition zone. The surface oceans might shrink very slightly. Nothing dramatic. Nothing you'd notice in a human lifetime, or even in 1 million human lifetimes. But the trend is there. Eventually, though, something will change that balance. Maybe increased volcanic activity will release more water than usual. Maybe a shift in plate tectonics will reduce the amount of subduction happening. The system will adjust. It always does. Earth has been balancing its water between surface and deep for billions of years. There's no reason to think that will stop anytime soon. But there's another factor to consider. The sun. Our star is slowly getting brighter. Not quickly, but over hundreds of millions of years. The sun's output increases. In about 1 billion years, the sun will be hot enough that Earth's oceans start to evaporate more rapidly. Water vapor will build up in the atmosphere. Some of it will be split apart by sunlight into hydrogen and oxygen. The hydrogen will escape to space. Earth will start to lose water. When that happens, the underground ocean becomes even more important. It's a reserve. a backup supply of water that's protected from the sun. Even as the surface oceans shrink, the transition zone will still hold water, locked away, safe from evaporation. It might be the last water on Earth, preserved in ringwoodite while the surface becomes increasingly dry. But eventually, even that water will be affected. As Earth continues to cool over billions of years, the transition zone itself might change. The temperature and pressure conditions that allow ringwoodite to exist might shift. The minerals might transform into something else. Something that can't hold water as well. And when that happens, the water will be released. It will rise toward the surface. But by then, the surface might be too hot for liquid water to exist. The water will evaporate and eventually be lost to space. So the underground ocean has a lifespan. It's not eternal, but that lifespan is measured in billions of years. For all practical purposes, from a human perspective, it's permanent. It will be there long after we're gone, long after our civilization has risen and fallen, long after humans, if we survive, have spread to other worlds or evolved into something different. The underground ocean will still be there, cycling water through the deep, maintaining the balance that makes Earth work. And there's something comforting about that. In a world where everything feels temporary, where change happens constantly, there's this massive reservoir of water beneath our feet that's been stable for eons. It's been there since before life existed. It will be there long after. It's not something we can touch or see or directly interact with, but it's real, permanent, a reminder that Earth operates on timescales far beyond human comprehension, that the planet has its own rhythms, its own processes, its own deep, slow heartbeat that will continue long after we're gone. Imagine if we could reach that underground ocean, if we could drill down and tap into it. 3 times more water than all surface oceans combined. It sounds like the solution to every water shortage humanity will ever face. Endless supply. No worries about droughts or depleted aquifers. Just drill down and extract what we need. But here's the reality. We can't. Not even close. And we probably never will. The deepest hole ever drilled is in Russia. A Soviet project called the Kola Superdeep Borehole. They started drilling in 1970 and kept going for over 20 years. The goal was to drill as deep as possible, to see what they could learn about Earth's interior. They reached about 7.5 miles down, just on 5 miles, and then they had to stop. Why? The temperature. At that depth, the rock was over 350 degrees Fahrenheit, much hotter than they expected. The drill bit kept overheating. The rock became so hot and soft that the hole tried to close itself. The equipment couldn't handle it. And that was at 7.5 miles. The transition zone starts at 250 miles down. That's more than 30 times deeper than the deepest hole ever drilled. Let's say we somehow solved the temperature problem. We invented materials that could withstand thousands of degrees. We still have pressure to deal with. At 400 miles deep, the pressure is millions of times what we experience at the surface. It would crush any drill we could design. The rock itself acts differently under that pressure. It flows like thick honey over geological time. Any hole we drilled would close up. the mantle would squeeze it shut like toothpaste in a tube. And even if we could drill that deep, even if we could somehow keep the hole open, what would we find? Not liquid water. Remember, the water in the transition zone is locked inside ringwoodite. It's part of the crystal structure. You can't just pump it out. You'd have to extract the rock, bring it to the surface, and somehow break down the minerals to release the water. That would require enormous amounts of energy, far more energy than the water would be worth. Think about the logistics. A hole 400 miles deep. That's a tunnel from the surface to deeper than the International Space Station orbits above us. Except we're going down instead of up. And space is empty, easy to move through. The deep Earth is solid rock. Hot, pressurized, flowing rock. Every inch of that tunnel would have to be maintained, kept open, prevented from collapsing. It would be the most difficult engineering project in human history. By far, the cost would be astronomical. We're talking about technology that doesn't exist. That might not even be possible given the laws of physics. And for what? To access water that we can't easily extract anyway? When we have oceans on the surface that are much easier to desalinate? It doesn't make sense. Not economically, not practically, not by any measure. But let's imagine, just for a moment, that we did it somehow. That we drilled down and tapped the underground ocean, started bringing water up. What would happen? For one thing, we'd barely make a dent in the reservoir. The amount of water down there is so vast that human consumption, even on a massive scale, wouldn't significantly reduce it. We could pump for 1,000 years and the transition zone would hardly notice. But there's another issue. That water has been down there for millions, maybe billions of years. It's in equilibrium. It's part of a cycle that regulates Earth's surface environment. What if removing large amounts of it disrupted that cycle? What if it affected plate tectonics, volcanism, the stability of Earth's climate? We don't know what the consequences would be, and that's exactly why we shouldn't try. The underground ocean is untouchable, and maybe that's for the best. Some things should remain beyond human reach. Some parts of nature should stay wild and unexplored. Not because we're not curious, not because we wouldn't love to study it up close, but because some systems are too big, too important, too fundamental to risk disturbing. The water in the transition zone isn't there for us to use. It's there because that's how Earth works. It's part of the machinery that keeps the planet habitable. That cycles water over geological time. That stabilizes the surface environment. It's doing its job perfectly well without human interference. And it will continue to do that job long after we're gone. So the underground ocean remains what it's always been. A hidden reservoir, massive beyond comprehension, locked away in blue crystal hundreds of miles below our feet, close enough to be part of the same planet we live on, far enough to be completely beyond our reach. And in a strange way, that's exactly where it should be. When you picture the underground ocean, you might imagine a continuous shell of water-bearing rock wrapped evenly around the planet. A perfect sphere of blue crystal sitting at 400 miles down. But the reality is more complex, more interesting. The transition zone isn't uniform. It's patchy, variable, a network of wet and dry zones that tells a story about how Earth's interior moves and evolves. Some areas of the transition zone hold a lot of water. Other areas hold very little. This variation happens because of how water gets there in the first place. Remember, water descends through subduction zones. Those zones aren't evenly distributed around the planet. They exist where tectonic plates collide. Around the Pacific Ring of Fire, along the western edge of the Americas, near Indonesia and Japan. In these regions, old ocean floor dives into the mantle, carrying water with it. That descending water doesn't spread out evenly. It stays concentrated along the path of the subducting slab. As the slab sinks deeper, it eventually reaches the transition zone. The minerals transform. Olivine becomes ringwoodite, and the water gets trapped right there, in the area above the descending slab. So, beneath active subduction zones, the transition zone tends to be wetter. More water-bearing ringwoodite, higher concentrations of the underground ocean. But not everywhere has active subduction. Large parts of the Pacific, for example, sit above mantle that's relatively stable. No plates diving down beneath them. These areas might have less water in their transition zones. The ringwoodite there could be drier. The underground ocean in those regions might be thinner, less concentrated. The variation can be significant. Some estimates suggest that certain areas might have 2 or 3 times more water than others. Scientists study this variation using seismic waves. When earthquakes happen, the waves they generate travel through Earth's interior. Those waves move at different speeds, depending on what they're passing through. Dry ringwoodite transmits waves at one speed. Wet ringwoodite, with water in its structure, transmits them slightly slower. By measuring these tiny differences across thousands of earthquakes, researchers can map where water exists in the transition zone. The maps they've created show a complex picture. Hotspots beneath the Pacific, where water concentrations are high. Drier zones beneath Africa. Variable concentrations beneath Asia. It's not random. The pattern follows Earth's tectonic history, where slabs have been subducting for millions of years. Water has accumulated. Where the mantle is older, more stable, water concentrations are lower. The transition zone is a record of plate tectonics written in water. But there's another layer of complexity. The transition zone isn't static. The mantle moves, slowly, over millions of years, but it moves. Hot material rises from deeper in Earth. Cooler material sinks. This creates currents in the mantle, circulation patterns that redistribute heat and material over time. And those currents affect the water too. Water that accumulated in one area might get carried slowly to another. A wet patch of ringwoodite might be transported by mantle flow toward a drier region. Over millions of years, the distribution of water in the transition zone shifts. It's dynamic, always changing, never quite the same from one geological era to the next. The underground ocean has geography, but that geography evolves. There are also vertical variations. The transition zone isn't just one layer. It's a range of depths from 250 to 410 miles. And within that range, different minerals exist at different depths. Ringwoodite dominates, but other minerals are present too. some hold water better than others. Near the top of the transition zone, conditions favor one set of minerals. Near the bottom, another set. Each has different capacities for storing water. This means the underground ocean has layers within layers. Near 250 miles, you might find high concentrations of water. At 350 miles, less. At 410 miles, where ringwoodite transforms into other minerals, the water gets released or absorbed into different structures. The transition zone isn't a simple reservoir. It's a complex, three-dimensional network of varying water concentrations that change with depth, location, and time. Understanding this network is crucial for understanding Earth's water cycle. The transition zone isn't just a passive storage tank. It's an active participant in how water moves through the planet. Some regions feed water back to the surface through volcanism. Other regions accumulate water from descending slabs. The network connects surface oceans to the deep interior in ways we're still figuring out. Every earthquake that sends waves through the transition zone gives us a little more information. Every diamond that brings up fragments of deep minerals adds to the picture. Slowly, we're mapping this hidden ocean, understanding its structure, its variation, its role in making Earth the planet it is. We can't go down to the transition zone, but sometimes the transition zone comes to us. Not often, not in a way that's easy to find, but occasionally through violent geological events, pieces of the deep make their way to the surface. These fragments are our only direct evidence that the underground ocean exists. They're messengers from a world we'll never visit. Diamonds are the most famous messengers. They form under extreme pressure, deep in the mantle. Most diamonds come from depths of around 90 to 120 miles. But some come from much deeper. These are called superdeep diamonds. They form in the transition zone itself, at depths of 250 to 400 miles, right where ringwoodite exists. When these diamonds crystallize, they sometimes trap tiny inclusions. Bits of the surrounding rock get caught inside as the diamond forms. Those inclusions are like time capsules. They preserve samples of minerals that exist at those depths. Minerals that would normally transform or break down if brought to the surface slowly. But locked inside a diamond, they stay protected, unchanged, perfect samples of the deep. The journey these diamonds make is remarkable. They don't slowly rise through the rock. That would take too long. The pressure and temperature changes would destroy them. Instead, they get caught up in explosive volcanic eruptions. Rare, violent events where magma blasts up from deep in the mantle at incredible speeds. These eruptions create narrow pipes called kimberlites. The magma races upward, traveling hundreds of miles in hours, so fast that the diamonds don't have time to change. They arrive at the surface still carrying their precious cargo of deep minerals. That 2014 diamond from Brazil was one of these messengers. The fragment of ringwoodite trapped inside it was the first physical proof that water exists in the transition zone. Before that, everything was theory, models, seismic data that suggested water might be there. But that diamond made it real. Scientists could hold it, study it, analyze its composition. The ringwoodite contained about 1.5% water by weight. That tiny inclusion changed our understanding of the planet. Since then, other diamonds with ringwoodite inclusions have been found. Each one adds to the story. Some contain more water, some less. Together, they give us a range, a sense of how variable the transition zone is, how much water different regions might hold. Every fragment is valuable beyond measure, not for its beauty or clarity, but for what it tells us about Earth's hidden depths. But diamonds aren't the only messengers. Sometimes volcanic eruptions bring up xenoliths, chunks of foreign rock carried from the mantle. Most xenoliths come from shallow depths, but occasionally deeper samples arrive. Rock that formed at the boundary of the transition zone. These samples are rarer than deep diamonds and harder to identify. But when scientists find them, they study them intensely, looking for signs of water, traces of minerals that only form at extreme depths. Each messenger, whether diamond or xenolith, is a gift, a window into a world we cannot access. These fragments have traveled further than any human will likely ever go. They've experienced temperatures and pressures we can only imagine. And they've survived the journey intact, bringing evidence of the underground ocean back to the surface. Without these messengers, we'd only have indirect evidence, seismic readings, computer models, theories about how Earth might work. But with them, we have proof. Physical, tangible proof that water exists in massive quantities in the deep, that the transition zone holds an ocean larger than any we can see. The diamonds don't lie. They can't. They're too hard, too durable, too honest in what they preserve. And they keep coming up, one at a time, each one carrying news from the depths. You learned about the water cycle in school. Water evaporates from the ocean, rises as vapor to the atmosphere, condenses into clouds, falls as rain, flows through rivers back to the ocean. The cycle repeats. Simple, clean, easy to understand. But that's only part of the story. The surface cycle, what we can see. The real water cycle is much bigger. It includes the deep. It operates on multiple timescales at once. Days and weeks for the surface cycle we all know. Millions and billions of years for the deep cycle we've just discovered. Both cycles are connected. Both are essential. Together, they make Earth the water world it is. Start at the surface. Rain falls. Some of it soaks into the ground. Some runs off into streams and rivers. Eventually, most makes its way to the ocean. That happens relatively quickly. Water spends an average of about 9 days in the atmosphere before falling as rain. It might spend years in a glacier or decades in a lake. But compared to geological time, that's nothing. The surface cycle is fast. Now add the deep cycle. Ocean water doesn't just evaporate and fall as rain. Some of it gets pulled into the seafloor. It seeps into cracks. It reacts with minerals. It becomes part of the rock through chemical processes. When that rock gets old enough, when it reaches a subduction zone, it descends. Down into the mantle. The water goes with it, locked in mineral structures. At first, as the rock descends, some water gets squeezed out. It rises back up, causing volcanism at the surface. But not all the water escapes. Some stays bound in minerals that hold it tightly. Those minerals keep descending, down through the upper mantle, eventually reaching the transition zone. There, the minerals transform into ringwoodite, and the lattice gets locked in even more securely. That water might stay in the transition zone for hundreds of millions of years. It's trapped, part of the deep reservoir. But it's not there forever. The mantle moves, currents flow. Eventually, that water-bearing ringwoodite might get incorporated into rising mantle rock. As the rock rises, pressure decreases. The minerals transform again, and the water gets released. That released water rises with magma toward the surface. It emerges through volcanic eruptions as steam. It enters the atmosphere, condenses, falls as rain, and rejoins the surface cycle. The water has completed a full loop, surface to deep and back again. The journey might have taken 100 million years, but it's complete. The cycle continues. This bigger cycle explains things the surface cycle alone cannot. It explains why Earth's oceans have stayed relatively stable in size for billions of years. Water is constantly being removed through subduction, but it's constantly being returned through volcanism. The rates balance. The total amount stays roughly the same. It also explains where Earth's water came from. Not all delivered by comets, as we once thought. Much of it has been cycling through the planet since Earth formed. The underground ocean is the main reservoir. The surface ocean is just overflow. Water that happens to be at the surface right now, but might cycle back down eventually. Understanding this bigger cycle changes how we see water. It's not just about rain and rivers anymore. It's about plate tectonics, volcanism, the deep structure of Earth. Every drop of water is part of a system that spans the entire planet, from the atmosphere to the deepest parts of the mantle, from seconds to billions of years, all connected, all cycling. The water in your glass might have fallen as rain last month, but before that, it could have been in the transition zone for 100 million years. And before that, part of an ancient ocean that existed when life first emerged. Water doesn't just move through space, it moves through time, cycling endlessly through Earth's many layers, connecting everything. Right now, as you rest there, think about where you are, not just the room you're in or the city outside. Think deeper, below the floor, below the foundation, below the soil and rock. Keep going down in your mind, through miles of crust, through the upper mantle, down to that layer 400 miles beneath you. There's water there, more water than in all the oceans you've ever seen. More water than in every lake you've visited. More water than in all the rivers that flow and all the rain that's fallen. It's sitting there right now, under your feet, under everyone's feet, a hidden ocean that's been there longer than anything living on the surface. You can't see it. You can't touch it. You'll never visit it. But it's real as the ground beneath you, as real as the water you drink. It's part of the same planet, part of the same system, connected to everything at the surface through cycles that span millions of years. Every time it rains, you're seeing water that might have been in that underground ocean once. Every time you fill a glass from the tap, you're touching water that might cycle down there eventually. The boundary between surface and deep isn't as clear as it seems. Water moves between them, slowly but constantly. The underground ocean isn't separate from your world, it's part of it. Think about the stability that ocean provides, how it's been regulating Earth's water supply for billions of years, how it buffers against loss, how it ensures that water stays on this planet instead of evaporating into space, how it makes Earth habitable. You're alive partly because that water exists down there, doing its quiet work, maintaining balance, keeping conditions stable enough for life to thrive. And think about the time. That water has been cycling for longer than complex life has existed, longer than plants have grown on land, longer than animals have walked or swum or flown. Some of those water molecules in the transition zone might be original, part of Earth since the planet formed. They've seen everything, they've been part of everything, and they're still here, still cycling, still part of the system. You're connected to that. Every person is, every living thing. We all depend on water, and the vast majority of Earth's water isn't where we can see it. It's hidden in blue crystal hundreds of miles down, locked away but not lost, present but not visible. A reservoir so large it defies imagination. And yet, somehow, it's real. So, as you lie there, comfortable and still, know that you're not just resting on solid ground. You're floating on a water world. Most of that water is beneath you, hidden, quiet, but there. It's been there since before you were born. It will be there long after you're gone, a permanent part of this planet, a reminder that Earth holds secrets in its depths, and the biggest secret of all is an ocean larger than any you can see. We started this journey at the surface, standing on solid ground, wondering what might be hidden below. Now, after traveling through hundreds of miles of rock, after exploring the transition zone and understanding the underground ocean, we return to where we began. But everything looks different now. The ground beneath you isn't just rock anymore. It's part of a system, a water cycle that reaches into the deepest parts of Earth. Every step you take, you're walking on top of an ocean 3 times larger than all the water you can see. That ocean has been there for billions of years, quietly doing its work, regulating, stabilizing, making life possible. The water you drink connects you to that hidden ocean, not directly, not immediately, but through time, through cycles that span millions of years. That water might have been locked in ringwoodite once. It might cycle down there again someday. Every drop has a history longer than human civilization, longer than our species has existed. Water is ancient, and it's patient. It cycles through Earth's layers at its own pace, unbothered by anything happening at the surface. This discovery changed how we understand our planet. It showed us that Earth hides its most important resources deep inside, that the surface is just one part of a much bigger system. That water, the key to everything living, exists in forms and places we never imagined. The underground ocean isn't just a scientific curiosity. It's fundamental to how Earth works, to why we're here at all. And there's something humbling about that. About knowing that beneath every continent, beneath every ocean, there's this vast reservoir we can't access, we can't control, we can't even fully measure. It exists beyond our reach, doing what it's always done, what it will continue to do long after we're gone. Some things are bigger than us. Some systems operate on scales we can barely comprehend. The underground ocean is one of them. So, as you settle deeper into rest, as your breathing slows and your mind quiets, hold this thought. You live on a planet that's mostly water, but most of that water is hidden, locked in blue crystal hundreds of miles down. It's been there since the beginning. It will be there at the end, and in between, it connects everything. Surface to deep, past to future, the first raindrop to the last. If you enjoyed this journey into Earth's hidden depths, I'd love for you to hit that like button and subscribe. Tomorrow, we'll explore another mystery that's been hiding in plain sight. And drop a comment telling me where you're listening from and what time it is there. Until then, rest well, let your mind drift like water through stone, and remember that beneath you, always, is an ocean pods larger than dreams.